Yes, thanks a lot. Hi everyone. My name is Philipp Geiger. Great pleasure to be here. So this is joint work with Michel Besserf, Justus Winkelmann, Claudius Preusel, and Bernhard Schöllkopf. And you can also find this slide on my webpage, pgeiger.org. Okay, so to motivate our study, I think it's clear that our collective systems face a lot of big challenges on the global level of societies, of course, but also on a more local level. So, for instance, our shared facilities, many of them suffer from congestion. So, citizen centers, you have long queues, or on road networks, you have a lot of traffic jams, overcrowded train connections, and so forth. Now, recently, data-driven methods have been introduced to provide forecasts to users of these facilities to allow them to use these facilities more efficiently to the extent this is possible. So, for instance, on the top left image here, you see Google Maps popular times. Maybe you have seen this for restaurants or a citizen office or whatever. It shows you, like, for each time of the day, how crowded the place will probably be. And similar, so some other examples from motorways and so forth in France. Okay, so I think these are interesting methods, but of course it remains to actually analyze and understand these methods. So I think there are various interesting questions. So first, under what conditions can these methods actually help? And here the goal is not just to provide a good forecast, but I think the end goal is really to support users to make a better coordination with other users in terms of really their personal preferences about when to go to the facility and the crowdedness level and so forth. And so how can we formulate this overall objective of coordination, and to what extent or under what conditions can we achieve it? And so this is a more principled study of what can be done. This is the first point. And as a second point, of course, we are also interested in, like, what specific algorithms can actually help, and can we have some, like, convergence or optimality guarantees. Okay, so let's have a rigorous model of the setting we are examining. So let's consider what we call the assistant-based system. So on the left side, we have the component of the system. On the right side, the components of the user, which are generally private, which means they are latent and not directly observable to the assistant. Okay, so as I already said, so the assistant provides a forecast A, and we assume generally this is a probabilistic forecast to have a general treatment. And this is given to all the users, and each of them, we assume, thinks this is a good forecast for how the other users behave, and chooses the optimal action under this forecast, so the optimal slot or time slot in a facility, given each his or her utility function. And so the utility can be, maybe some people have a specific time restriction when they can have to go to the road due to their calendar and don't care so much about crowdedness, but a little bit. Or others don't care about the time, but just want to have the least crowded time in a cafeteria or something. Okay, so let's make this a bit more rich. So I think it's fair to say that usually the assistant also has some covariates, like day of the week, or the weather also to make the forecast. And of course also the users have some private signals, so they know when they are hungry, so they understand their utility function to some extent, and also they know what their calendar says and so forth. Okay, so now for this setting, for this system, like on the one hand, let's consider like the classical prediction accuracy objective, or a version of it. So this is simple and it's directly observable, right? So this is just to minimize the distance between the forecast, the distribution, and the actual outcome, like the actual distribution of y for each possible state of the covariate. Of course, the forecast influences the outcome, so this both depends on pi. And sorry, I think I forgot to mention, so as I said, the actions B may not be directly observed by the assistant or the loss function. So we have this outcome Y, and we assume this is something publicly observed. This can be an aggregate of the BI for privacy reasons, for instance. Okay, and just to mention later, we also consider a dynamic version of the setting where this system repeats every day, basically, indicated by the gray arrows here. But for now, let's consider just this, because this is enough for now. Okay, so as I said, in the end, we want to achieve coordination. And how can we make this objective actually rigorous? And the way we do it in this paper is as follows. So let's consider, let's start from the same system again, but let's just drop the assistant. And let's instead assume that the users kind of know everything, like up to probabilistic beliefs they could know. So they know like what the distribution over the utility functions of the other people. And also we assume that they are all fully rational, so they have full inference capacities and so forth. And so now the idea is, okay, so this we call the benchmark Bayesian game, because this is, by definition, can be seen as a Bayesian game, G. And yeah, it helps us as a benchmark to assist evaluate the assistant. And okay, so based on this, we can now define an objective which actually more captures the idea of coordination based really on the user's preferences. So this is, the idea is that for any user behavior that can occur in the assistant-based system, so this is this pi of bi given wi, the whole tuple of users. So this is a strategy profile in the game sense. We can plug it into the we can plug it into the Bayesian game, and we can check if this constitutes a Nash equilibrium of this idealized setting, which ideally one would like to achieve maybe. And so for those of you who don't know Bayesian Nash equilibrium, roughly the idea is that everyone has their utility, and kind of if the others would be fixed, one takes the optimal action. And if this is true for everyone, this is a Bayesian Nash equilibrium under some beliefs. Okay, so this is the setting and the objectives we consider. And now, as I already indicated, so the first thing is a principled analysis of what can these forecasting or predictive assistants achieve for this coordination objective. Okay, so the first result here we call self-fulfilling prophecy characterization. So we make two additional assumptions and some details. So the first one is, let's assume that the users do not know more about each other, like when they're hungry or their calendar, than the assistant knows about them. So this is this conditional dependence. And second, let's also assume that kind of the forecast y or the variable y together with the private signals contains enough information about the utility function so that this latent state, sorry I didn't mention, so there's this latent state which can have some influence in principle on the utilities, but we say, okay, we don't need this anymore, this contains enough information. So under these assumptions, we can say that if the assistant achieves really the perfect thing it can achieve with respect to the prediction objective, so it kind of perfectly matches, the forecast matches the outcome, which can be considered a self-fulfilling prophecy because there's a feedback loop from forecast to outcome, then we can show that the Bayesian Nash equilibrium, that the resulting user behavior actually constitutes a Bayesian Nash equilibrium, so it's kind of a solution of the coordination problem in this perspective. So this is the first result, and as the question that remains, of course, is when do these self-fulfilling prophecies exist? Because it could happen that if I make a forecast and all users have the same utilities, they all jump to the same empty slot, so I could not find a forecast which becomes true. So as a second result, we consider we have several settings in the paper, but let's consider this one setting. So here we consider a continuum of users, almost specifically in the name of, in the wording of game theory, types of users. And this corresponds to a non-atomic game, for those of you familiar. And this models well a setting with many users and is mathematically nice to analyze. Let's assume V and V are constant. Let's assume what is observed is really just an aggregate of how many users take a specific slot. And additionally, we also need to assume that the utilities are a polynomial, and this polynomial strongly depends on the user type, so there's some diversity which cannot cancel out in a sense. Under these assumptions, we can prove actually that a self-fulfilling prophecy exists, so perfect prediction. And the proof is based so that we consider A, which are distributions on this Y, and to make them compact, we consider the weak star topology and then apply the Leray-Schauder Tikhonov fixed point theorem, because we can also show that the mapping is continuous. As a corollary, we also get a Bayesian-Nash equilibrium existence result for non-atomic games, which to the best of our knowledge is also not known. Okay, so this was kind of what can in principle be achieved with these assistants. So let's also look a bit more into which algorithm achieves these optimalities. Okay, so so let's look again at this assistant-based system. I simplified it a bit, I dropped some variables. And so now, as I already indicated, let's look at the repeated version. So the assistant always gets so this is a dynamic system, and each day the assistant also sees like the forecast and the outcome of yesterday. Furthermore, assume in this large-scale setting I showed previously that the utility functions are linear, and because this allows us to actually have a point forecast being already enough, and we don't need a probabilistic forecast. Now for this setting, we propose the algorithm expodamp, which is quite simple. So at each stage t, just take the forecast from the previous action and correct it a bit towards the outcome by factor of alpha. So this is a well-known formula from time series forecasting, but it hasn't been applied to the setting when the forecast influences the outcome. So for this algorithm, we can actually show that it converges exponentially against the self-fulfilling prophecy. So the users converge against the Nash equilibrium, where the alpha has to be in some interval. So these are some details which you can look up in the paper. So we have some guarantee, and we also have a stochastic result, but I don't show this here. So also besides the theory, we did some large real-world experiment, some interventional experiment in our campus cafeteria in Tübingen in Germany, where we actually like programmed an app and installed sensors and everything, and expodamp provided like the forecast actually to our campus. So there are 400 users of the cafeteria. And so there we could also see that expodamp outperforms the baseline, and the baseline was based basically on an IID assumption and not taking account this control loop. Okay, so this was the algorithm and the guarantees we have. So basically, let me briefly also talk about related work. So overall, I think this is really a rather new setting. So there's not so much yet. So closest related on the game theory side is learning in games and learning congestion games. And this relates closely to the talk we've previously seen about all these dynamics and best response dynamic. But usually they don't consider an assistant, with the previous talk maybe being a bit of an exception. Then there's control theoretic work in smart cities research, which they do consider an assistant. In this sense, it's quite similar to us. But they don't consider that users have a priori unknown individual utility functions. So they just fix some utility functions, say like everyone doesn't want to have a crowded thing and avoids it. And then they give recommendations, but I think this is not always realistic because maybe some people even like to go to crowded places. Then like on a much broader level, I think mechanism design and social welfare optimization, as we've seen before, are related, and also fairness methods, in a sense they are all kind of solution concepts for collective problems, I guess. But so I think these are also interesting to investigate for this setting. But the advantage of our thing is that we can at least identify the optimal solution from the sparse behavioral data we have. And also we have some robustness with respect to gaming, because asymptotically we reach a Nash equilibrium, and this by definition is the kind of optimal thing. No one can improve from it. So in some weak form of incentive compatibility. And okay, so I mentioned this algorithm in the beginning, Google Popular Times and so forth. And here I have to say that I don't know the algorithm they use. It would be interesting. I tried to reach some, but so far I didn't get knowledge of this. And yeah, some parts of the paper, just to mention this, were omitted, like another algorithm and also some more stochastic Kalman filtering setting for the exponent. Okay, so let me wrap up. So this research is part of what I think is an interesting, rather new direction of machine learning for collective challenges. And I think it's particularly interesting because we need concepts and an analysis which is aware of the social context in the sense of what utility do we actually optimize, or what fairness criterion or whatever. And also in the sense of, okay, there are multiple agents, we influence them, they may kind of try to game us or something. Here we considered the more specific scenario of this predictive assistance for the shared facilities to use them more efficiently to the extent this is possible. And we use the game theoretic view with game theoretic solution concept Nash equilibrium, and we also propose some algorithms which have guarantees. And okay, so I think this is, as I said, a rather new direction with potentially many more mechanisms based on machine learning which can help there, and with an interesting analysis. So thanks a lot for your attention. Yeah.